Hi, welcome to the introduction to boundary layers. So like we said, we're going to do a brief overview of fluid mechanics, some fundamental equations and some concepts in the first two modules, right? And let me start by posing the question that a fluid can flow, right? A solid cannot, right? So let's kind of think about that a little bit, okay? Now, this thing is a solid, as you see, this thing is a solid. This whole thing that I have here, this is basically a bunch of coasters, right? And this thing is a solid, and this cannot flow, right? You have a bottle of water, you move the bottle, the water in the bottle moves, but there's no flow exactly, right? It's not like you open your tap and the water flows. So what is it that, what's up with that fluid flows where a solid cannot, right? And if now let me do one thing. Let me take out all these coasters from here. Let me take this out. Okay, let's keep this aside. Now this is like a set of coasters, right? Now these are separate. As you can see, these are all separate. Now holding them together. Okay. Now say apply a force, then these things kind of move at the same time. Now let me do a thing, okay? What I will do is I will, hold the bottom ones, I'll try to fix it, right? And I won't let the bottom ones move. I won't let the bottom ones move. So when I apply the force, what happens? What happens? Right? So I'm not letting the upper ones, the bottom ones move. So what basically happens is that the top ones, the top layers move forward. So this is nothing but a flow. So if you think of a fluid, which consists of so many layers, then as it say moves over a surface, I'm going to exaggerate this a little bit. As say it moves over a surface, which could be so many things. It could be a flat plate, it could be moving through a pipe, it could be moving over an airplane wing, so on and so forth, right? So, your fan blade. So when that happens, so basically you can consider the fluid to consist of layers like that, where one layer slides over the other, right? And this is what causes flow. Right, this is what causes flow. Now, if you were to just look at it from this side, and join these points, it might give you, so join these points in the sense that with respect to, the origin here, this has moved slightly forward, this has moved slightly forward, so on and so forth. So if you kind of draw this a little bit like that, it's something familiar. You're kind of familiar. So let us sort of talk about this a little more. So this whole force that I'm applying, right? This force which I'm applying, which is making these layers, each layer to slide over the other. This is nothing but basically shear force, okay? So it is the shear stress that we're going to look at, okay? So let us see a little bit. So how much shear force can cause how much of movement, and how do we relate that in terms of a fluid, right? What is it? Is it about a fluid property itself? What does that depend on? Let's sort of go and look at that a little bit, okay? All right, so so say we're basically looking at say fluid flowing over a flat plate. Right, so we've got a flat plate, so we got a flat plate like that, okay, and yes, this is stationary, of course, right, and so we have let's just consider a fluid element like that, right? If I consider a fluid element like that, so now what we will do is that this fluid element, however, now is going to deform a little bit, right? How is it going to deform? Now, as we just said, the bottom, right? The bottom part of this fluid element is going to stick to this. The top part, however, is going to move forward. You know, the layer, so you can think of this here again as, you know, layers. You can think of these as layers. So these layers are going to sort of move forward. So let's say that it deforms by something like this, right? And by an equal amount here, that, okay? So what we're going to do is, let's go ahead and name these, okay? So let's just say that this bit that we did, right? This is delta theta, okay? Similarly here, this is delta theta, right? So this blue thing, the blue is basically the shape of the fluid element at t is equal to t naught, t is equal to 0, say, right? So this is at t is equal to 0, and this is essentially t is equal to at a certain delta t, okay? Let us call this as A, okay? This is B, and this is C, right? This is C, and this distance, so this distance that we have, okay, this is, say, S. This is S, and this, sorry, that should be a straight line, okay? So that is delta y, okay? And the fact that this moves, okay, it flows with respect to, and things are changing, there is a certain, you know, displacement happening over a time, there's a certain velocity. So let's say that velocity, so this velocity is, of course, is equal to, say, we can call it delta u. So this is essentially a fluid element, you know, a simplistic fluid element flowing over over a flat plate, okay? Should I sort of write that? Okay, so this is essentially fluid flow, okay, over a flat plate, okay? Fine. Now let us look at the triangle, okay? I'm going to write it here. Now, if you see, so from the triangle ABC, okay, from the triangle ABC, what is tan of delta theta? What is tan of delta theta? Can you see? This is A, B, C. So tan of delta theta is this S by delta y. Is that fine? So S by delta y, right? And this S is basically the entire displacement. And then, like we said, the displacement, so the corresponding velocity is delta u, and the time during which this has happened is delta t. So I can also write this as the corresponding velocity time by delta y. Is that right? Right? Now, of course, here the changes are infinitesimal, okay? So, since changes are infinitesimal, okay? I've got the spelling right, okay? So what can we write? We can basically say that tan of delta theta, I can write that as delta theta, isn't it? So therefore, delta theta is equal to delta u, delta t, delta y, right? Or delta theta by delta t is equal to delta u by delta y. Okay, now from what you can see here. Now, here of course theta, and theta is changing only with respect to time, right? Theta changes on, theta is a function of only time, and u is a function of only y. So because we're not really looking at the change of u with respect to the x-axis, right? So u is, so therefore these partial derivatives, I can actually write this as derivatives, okay? So therefore this, right, I can write this as d theta dt is equal to du dy. I can write that, okay? Now that's something we get. Now what is this d theta dt? So what you can basically see here, that d theta dt is, is basically giving you a quantitative measure of how much the fluid element is deforming, right? So therefore this is essentially the strain rate. Okay, so this thing, this d theta, right, this thing, so this thing is essentially nothing but strain rate. Okay, that is nothing but strain rate. Okay, now that we have here, so now the next question is that what exactly decides the strain rate? What does the strain rate depend on? In the sense that I do have a fluid element, so what tells me that how much will be the deformation, or what exactly does that depend on? So let's sort of go to the next page. Okay, now as you must also be aware that shear stress, right, is proportional to the strain rate, right? In this particular case, in the case of the fluid, so d theta by dt is equal to du by dy. So therefore this means that, so I can write this, or shear stress, okay, let's denote that by tau, is proportional to du dy, okay, which is basically the gradient of the horizontal component of the velocity in the y direction, okay, horizontal component in the y direction. Okay, so this is where basically I think you're familiar with this. So we're going to introduce a coefficient, okay, coefficient of proportionality, or basically say that tau is equal to, okay, tau is equal to nu du dy, okay, du dy. So this is essentially nothing but, so this is something that you know, right? I think you know this. So this bit is nothing but coefficient of viscosity, right? This is coefficient of viscosity. So simple, all right? So if I were to, for example, so therefore, like I was saying, that the layers of the fluid move with respect to each other. So for example, say if I were to kind of draw a velocity profile, right? If I have a velocity profile, so say I go away from the plate, so this is say x, so I may have a plate somewhere here, okay? I may have a plate somewhere here, and this is essentially the y direction. So let's say I have a plate, so I have a plate maybe resting somewhere like that. So what I'm looking at is, so what I'm basically looking at is some kind of a velocity profile. So say the velocity profile is something like that, something like this, okay? And here, so essentially this bit is nothing but the velocity, right? And this depends on the y offset basically, right? So therefore, now now the thing is, so here, okay, so if I take a point here, right, if I take a point here, so, and I'm trying to understand the slope of that, okay, if I try to understand the slope of that, okay, I mean, I kind of exaggerate that. So I can basically say that this is du and this is dy, right? So this here. So this essentially means, so the slope of this velocity plot has du dy, right? Now this essentially, this basically means that if I have a little fluid, if I consider a fluid element, right? So this is my plate, I have fluid coming in. So this is my plate and I have incoming fluid like that, right? So at a certain point, you know, we just took this origin somewhere and the velocity plot kind of looks like that, okay? The velocity looks like that. So there, at some point, you know, we took the slope, you know, which basically means that, you know, going away from the plate at this point, if I take a little fluid element, then it would be it would be having, you know, a shear stress, you know, shear stress, which is equal to, right? So physically that basically means that here if I have a fluid element, then the slope of the velocity curve, mind you, the slope of the velocity curve will essentially give you a measure of the shear stress, okay? Shear stress. So shear stress is basically the coefficient of viscosity multiplied by the slope of the velocity profile, okay? Now, sort of let us just do just a simple, you know, problem before I go into something else. So, for example, okay, let's go to another page. Now, for example, I have say that. So I have x. These all should be straight lines. Okay. Hopefully, by the end of this class, I would be more good at doing this. Okay. So say I have. This is a very simple sort of plot. So this is a velocity plot again. Okay, this is a velocity plot, and this is, like I said, this is a velocity plot. So this is 0 and this is equal to v. Okay, capital V it is given, and this is h. This height is h. Okay, now this v is given to be 3 meters per second, h is equal to 2 centimeters, right? The question is find tau, right? Find tau. So how do we go about sort of doing this? Okay, well, I'll go about it one particular way, but I think you can do it another way as well. You know, I'd let you think about that. Okay, now. What I'm going to do is find out an expression. I'm going to do it a little bit like a mathematical way. I would like you to do more from your understanding of the definition of shear stress. Okay, so let me do that. So here what I can see is that the velocity, right, the velocity is a linear curve. It's basically a linear straight line. So it's equation of a straight line. So so I'm going to say u is equal to a plus by, where a and b are constants. Okay, it's basically a straight line. This is the equation of a straight line. Okay, then at y is equal to 0. Okay, u is also equal to 0, right? Which means that means 0 is equal to a plus 0, which means that a is equal to 0, right? Then at y is equal to h, u is equal to v. So this means that u is equal to v, a is 0, we got that. So this is b into h. So this means b is equal to v by h. Okay, so therefore we can write u to be equal to v by h into y, right? U, so this is u is equal to v by this, right? Then like we we just did, so tau is nothing but nu du dy. So from here, from this, say let's call this say 1, right? So from this expression 1, du dy is nothing but v by h. So therefore tau is equal to nu v by h. Okay, now v by h. Okay, that's the expression. Now I kind of did a little bit of math, and I got this, but I would I would request you to kind of think about this from a more conceptual basis. Okay, that we kind of, let's see if I can go back. Like I said, that that if I had to find out the stress is basically equal to nu du dy, and this is the slope of the element here, at this location, and how shear stress is proportional to the strain rate. So I would request you to go look at this, not sort of do this a plus by, not do it more mathematically, but think about that, find out maybe the slope or something. Okay, so find out that way. So do this, do the same exercise, a simple exercise, but do it anyways. Okay. Okay, so now there's something called Newton's law of friction. Okay. Now this viscosity, we'll come to the point that what does exactly. So I guess we've just said that it's a coefficient of viscosity. So what you can understand here, that fluid flow essentially is happening because of viscosity. So viscosity plays a very important part, and friction is something that we use more for solids, and friction in fluids is basically viscosity. So it is a measure, right? So like I said, coefficient of viscosity is essentially the shear stress, right, which is causing a corresponding strain. Okay. Now there is something very interesting here, which is important to understand, because what are the effects of considering viscosity? There are various fluid flows where we will not consider viscosity. The effect of viscosity is not dominant, so we kind of tend to ignore that. But if we do, then what kind of stuff exactly is, what should we know, or what are the things that affect? So that's what we kind of trying to discuss here. Okay, so now say I'm going to look at this. Okay, that and this. Okay, now again, this is basically, you can think of that as a velocity profile. Okay. Okay, and is that right? Yeah, okay, fine. Right, now let us consider, I'm going to consider a fluid element here, okay, and this fluid element is A. Okay, I'm going to consider two more fluid elements. Here, right, and this is B and this is C, right? So now this thing, right, this thing is moving with a velocity u A, right? This thing is moving with the velocity UB, this thing is moving with the velocity UC. Essentially, these two are moving with the same velocity, U naught. Okay, this is the thing. So essentially, so you have free stream velocity. Oh, sorry. So this is free stream velocity, which comes in here. Okay, so this is free stream velocity, and so you have a particle. So you have a fluid element A, which moves with the velocity UA. You have two more particles, UC and UB, which move, which basically UC is equal to UB, right? Which is, so UC is equal to UB, which is equal to U naught. Okay. Okay. Now, so therefore, let us also now look at the momentum, right? The momentum of the three particles. Okay, of the three particles. Now then, so this one, so momentum of particle A is MAUA, right? And we're going to say that all the three particles or all the three fluid elements have the same mass. So it's going to be M of UA. Okay, then there'll be MB UB, right? And that is equal to M U naught, and MCUC is equal to M U naught, right? So therefore, what we see is that if this is a velocity profile, right? So this thing that you have here is a velocity profile, this inclined line, right? This is showing a velocity profile. So if you have a particle A, fluid element A, which is kind of closer, right, to the, so you could probably have a plate or something here, right? You could have a flat plate somewhere over here. So now you have this particle which is located at some height, okay, and you have two more particles which are located somewhere up there, okay. And what you see is now this sort of a thing, this sort of a velocity profile, you know, this is happening because of viscosity, right? It is a viscous effect which is making, you know, the bottom of the, you know, fluid to stick to it, and the other layers are subsequently gliding over each other or sliding over each other. Now, when that happens, what you see here is that the momentum of this particle is M of UA, and momentum of these particles is M of U naught. So clearly, as we go from, say, you know, let's put some height here. So say this is H1 and this is, say, H2. So as we go from, say, H1, so as we go from H1 to H2, right, there is a change in the momentum. So therefore, and in all probability, U naught is larger, right? U naught is larger than UA. So if that happens, so therefore you have a higher momentum as we go away from the surface, you know, from the plate. So therefore, it is the viscosity which establishes, right, a momentum transport. But this momentum transport is in a direction which is perpendicular to the direction of flow. Understand that, because the direction of flow is this way, right? This is your U infinity, and this is how it is flowing, and the transport of momentum is this way, right? So so therefore, it is the viscosity. Let's write that down. Okay, it is the viscosity, right, which establishes. This is the viscosity which establishes momentum transport, right? Momentum transport in a direction perpendicular to the direction of flow. Okay, so therefore viscosity is also called a transport property of the fluid, right? So it's a transport property of the fluid, and it depends on both temperature and pressure, right? And it's a physical property of the fluid. It's a physical property of the fluid, right? And it depends on both temperature and pressure. The temperature dependence is quite dominant. Okay, so having sort of done that, okay, let me see if I should. Okay, there's just one more thing that I would sort of like to do, and okay, so that should take care of it for this module. Okay.